This is a preface to the original video I recorded for power analysis of regression coefficients. The program creates customized power tables for you based on different effect sizes and sample sizes that you want to explore. When I originally wrote the R code for the program, I structured it so that your requested table had to have 5 rows and 5 columns. The original video discusses power analysis assuming this. Since then, I've rewritten the program so that your table can have as many rows and/or columns as you wish. You can have 2 rows and 7 columns, 2 rows and 2 columns, whatever. The concepts in the original video hold, as do the basic instructions for how to use the program. You just have a bit more flexibility. I'm going to start the original video now, but keep this one revision in mind. In this video, I'm going to show you how to use the power analysis program for a regression coefficient in a linear regression. The button for it is down here. I'll click on it. When I do, a full set of instructions for how to use the program appears in the description box. We'll be inputting information into the input values box here. Before we do that, let me provide you some context for the program. The program conducts a power analysis using linear regression. I often use it to gain perspectives on statistical power for specific path coefficients in a complex causal model, as I'll illustrate to you shortly. To be sure, it yields only approximations to power in full information estimation (SEM), but it often is serviceable, and if anything, it's conservative. See my book for details and the qualifications. I also discuss in my book how to conduct localized Monte Carlo simulations in M+, to gain more precise perspectives on statistical power. To conduct a power analysis, you need to specify what is known as a minimally meaningful effect size. A minimally meaningful effect size is the smallest effect size that you think is theoretically, practically, or clinically important. For example, suppose there are sex differences in the starting salaries of assistant professors at major universities. Suppose that males earn on average $70,000 and females earn on average $69,995. All of us would agree that this difference of $5 per year is non-consequential, and we would not care if we failed to find a statistically significant effect, even though technically the null hypothesis is false. But what about a difference of $1,000? How about $2,000 or $10,000? What is the minimally meaningful effect size you want to be sure not to miss in a significance test? I discuss in my book how to make such decisions, but I do not consider the matter here. Specifying a minimally meaningful effect size is complicated, to say the least. In the current program, you work with a minimally meaningful effect size framed as the proportion of unique explained variance for a target predictor in a regression equation. For example, what is the sample size needed to reject reasonably often the null hypothesis for a regression coefficient for a predictor that accounts for, say, 5% unique explained variance in the population? What is the sample size needed to have sufficient power to reject reasonably often the null hypothesis for a predictor that accounts for 10% unique explained variance? And so on. Because linear regression is a general method that can work with continuous predictors, categorical predictors, and covariates, it's quite flexible for power analysis purposes. Given this, I think you will find the current program quite useful. I'm going to work through numerous examples. I will often orient my analysis of minimally meaningful effect sizes to Cohen's concepts of medium effect size, but this in no way means I endorse using his criteria. For details and a relevant critique, see my book. Now, to put this in the context of SEM, I want you to consider the following model. This is a model for a randomized explanatory trial in which a treatment influences an outcome Y. Treatment influences the outcome Y through 3 mediators, M1, M2, and M3. The treatment influences each mediator, and each mediator in turn influences Y. There's a causal relationship between mediator 3 and mediator 2, and there are covariates that I want to control for in the context of the analysis. These are indicated by cov1, cov2, cov3, cov4, and cov5. Finally, there are the disturbance terms, D1 through D4. This influence diagram can be translated into a set of linear equations. And the way you do that is you first identify the endogenous variables in the system, and then you specify a linear equation for each endogenous variable. As I discuss in my book, an endogenous variable is any variable that has an arrow going directly to it. That is, it has a cause in the system. So in this case, y is an endogenous variable because it has multiple arrows going to it from other variables in the system, M1, M2, M3, cov4, and cov5. M1 is an endogenous variable because it has an arrow going to it from the treatment versus control dummy variable. M2 also is an endogenous variable, as is M3. The treatment versus control variable is not endogenous. It has no causes in the system. We call it an exogenous variable given that. The same is true of cov1, cov4, cov5, cov3, and cov2. Because I have the 4 endogenous variables, I'm going to have 4 equations, and I've expressed those down here. The way you express an equation is you say that the endogenous variable is a linear function of all variables with arrows pointing directly to it. So y is a linear function of M1, M2, M3, cov4, and cov5. And you can see that I've put a linear model here with the intercept and slope terms. M1 is a function of the treatment versus control condition, covariate 1, and the disturbance term. And I've written the regression equation for it here. The same is true for M2 and M3. To determine sample size, I do a power analysis on each predictor and each equation, and then I use a sample size for the equation that produces the largest n. Sometimes I simplify this process by focusing only on the coefficients that I think will be the most sample size demanding. That is, where the minimally meaningful effect size is lowest, where the overall squared multiple correlation of the equation is lowest, and where there are the most predictors. I obviously give priority to the mediators in the treatment versus control variable in doing the power analysis for each equation. As you will see, the program lets you generate your own customized power table in which you specify 5 sample sizes and 5 effect sizes that you want to explore. Setting the model aside, I'll now show you several different applications of the program. Let me begin by analyzing power for the effect of a binary treatment condition, treatment versus control, on outcome means. That is, I focus on a mean outcome difference between the treatment and the control groups. Suppose I decide that my minimally meaningful effect size is a Cohen's d of 0.50, or what Cohen calls a medium effect size. It turns out that when there are no covariates in the equation, a Cohen's d of 0.5 translates into an effect size of 5.9% explained variance, which I'll round off to 6%. For program input, this first box specifies the squared multiple correlation for the full equation with all of its predictors. In this case, I have just one predictor, so the full equation is the one predictor. I enter the value 0.06, and I'll go ahead and indicate down here that I have one predictor. The second box specifies 5 effect sizes that I want to explore in the table. The effect sizes are specified by how much the full R-squared will reduce or drop if I eliminate the target predictor from the equation. In this case, because there's only one predictor, the reduced correlation must be 0. I have to specify 5 values for the program to work, so in this case, I'm going to put in 5 zeros because I have no choice. I can't vary the effect size with one predictor. In this box are the sample sizes that I want to explore. The program gives you a set of default sample sizes, but I can change those if I want to. I'll have an alpha level of 0.05, and I'm set to go. I click Register Input to generate the syntax. The program generates the syntax here. I copy it to the clipboard. I open up R. In R, I'm going to hit Control V to paste the syntax, and as the syntax is pasted in, it will execute. The commands appear in red and the output appears in blue, so I want to focus on the blue. This entry is a reminder that the full equation r squared was 0.06. This is what the r squared is reduced to if I drop the predictor. And these are the different sample sizes here. The table entries are the estimates of power. So you can see that for a sample size of 100, my power will be 0.706. For a sample size of 125, my power will be 0.8. So to achieve a power of 0.8, if I decide that's my standard, I'm going to need a total sample size of 125. And given that I have two groups, I'll have a sample size of about 63 per group. How about if the effect size that I want to evaluate is a Cohen's d of 0.2, or what Cohen calls a small effect? It turns out this translates into an explained variance index of 0.01, or 1% explained variance. So let me close R, and we'll go back and evaluate that scenario. In this case, I changed the r squared for the full equation to 0.01, and everything else can remain the same. I click on Register Input to redo the syntax. I copy it to the clipboard. I open up R, and I'll hit Control V to paste the syntax in. And here's the table. You can see that for a sample size of 100, to detect a small effect size as defined by Cohen's d, I'll have a power of 0.169, which is inadequate. In fact, when I look through this table, I can see that all of the power values are too low and not satisfactory, that my sample sizes that I specified are not large enough. So I'm going to rerun the program, but this time increase the sample sizes so that I get in the ballpark of a 0.8 power. I'm going to close R, come back up to the input box, and I'm going to change the sample sizes to 400, 500, 600, 700, and 800. I'm going to click on Register Input to regenerate the syntax. I'll copy that to the clipboard. I open up R. I'll hit Control V. And here's the table. I still see a predominance of low power estimates. And what stands out to me is that for a sample size of 800, I will have power of about 0.8. That means that in order to detect a small effect size, as defined by Cohen's criteria with power of 0.8, I'm going to need a total sample size of 800, or about 400 per group. Okay, let's consider another scenario. I'm going to close R and come back to the input box. Now let's suppose I have two covariates that I think account for about 20% unique variance. Now the full equation effect size is 0.20, which represents the two covariates, plus 0.06, which represents the effect size I'm targeting for my power analysis. So the total of those is 0.26. So I'll change this to 0.26. I'll put the original sample sizes back in. I now have 3 predictors instead of 1. And now I can vary the effect sizes because I have more than one predictor. For example, I might enter the reduced squared R's if I drop my target predictor by the following numbers. This first entry reflects an effect size of 2% unique explained variance. Because the full R-square was 0.26, when I drop the target predictor, it goes down to 0.24. That represents an effect size of 2% unique explained variance. The second entry is 3% unique explained variance, 4%, 5%, and 6%, which is what I'm interested in for a medium effect size. I'm going to click Register Input. I'll copy it to the clipboard. I open R. I'll hit Control V to paste. And here's the table that I get. Now the first thing I notice in this table is that for an effect size of 6% unique explained variance, that is where 0.26 is reduced to 0.2, I'll achieve about 80% power with a sample size of 100. This contrasts with the sample size of 125 from the first analysis that we did. This reflects a basic principle I discuss in my book, namely that you can increase power not just by increasing sample size, but also by including strategically selected covariates that account for variation in the outcome. I also show this in the video on the interactive simulation page of my website. Suppose for a variety of reasons I'm able to get a sample size of 150 for this study. In statistics, there's a concept called effect size sensitivity, and I often seek to use it when I report power analyses. Looking at the table, I can ask what effect size is associated with a power of 0.80 and a sample of size 150. It is 0.22, which corresponds to a unique explained variance of 4%. This is my effect size sensitivity. I'll be able to detect with power of 0.80 an effect size of 4% unique explained variance or greater. Now you might find that after examining an initial table, you may have to generate a new one with different sample sizes or different effect sizes to zero in on the types of statements you want to make. The program's useful because you can literally create customized power tables to fit your needs. Okay, let's consider another scenario. So I'm going to come out of R and go back to the input values. Now let's suppose I'm predicting an outcome from 5 variables, and my target predictor is a continuous mediator within this equation. Suppose I think the overall population R squared will be 0.40. That is, when I predict the outcome from the mediators and covariates, I'll have a squared multiple correlation of 0.40. And suppose I want to explore different effect sizes for the target mediator in terms of power. I might enter in the following values. The first value reflects 3% unique explained variance. The second one is 5%. The third one is 7%. There's 9% and 10%. So I'll be exploring those different effect sizes. I'll go ahead and use the default sample size estimates. And now I have to change the total number of predictors to 5. I click on Register Input. That generates the syntax. I copy that to the clipboard. I open R. I hit Control V to paste the syntax. And here's the table. Notice in this table that an N of 100 has an effect size sensitivity of 5% unique explained variance. You can see that right here. Okay, and the 0.35 is 5% explained variance, and that's virtually 0.8. A sample size of 175 has an effect size sensitivity of just less than 3% unique explained variance. I can get fine-grained estimates of the effect size sensitivity for an N of 175 if I regenerate the table, but use effect sizes just below 0.03, such as the values of 0.375, 0.377, 0.380, 0.385, and 0.390. An important perspective to have with power analyses is that they invariably make simplifying assumptions, and in this sense they can be considered as idealized representations that only approximate true data analytic scenarios. Power analysis programs typically do not take into account non-normality, missing data, outliers, and the use of coarse measures, to name but a few of the potential assumptions or complications. I want to end this video by just emphasizing that I think the strongest approach to power analysis is conducting localized simulations, a strategy that I discuss in my book. In sum, I think you'll find this program useful in giving you perspectives on statistical power. Okay, that's it. Thanks a lot.